Welcome to this explainer. Today, we're taking you from absolute zero to advanced process control. If you're an engineering student, a tech, or just starting out in automation, we're going to completely demystify what's going on inside those pipes. By the end of this, you'll be able to look at a control room screen and instantly know exactly what the physical hardware is sweating out in the field. Let's get into it.
Okay, quick look at our roadmap. We'll hit the core process building blocks first, learn to read response curves, nail down that essential control room vocabulary, explore the 4 process control modes, look at industrial transducers, and finally, figure out how to properly size and select valves. Starting with Section 1, Core Process Building Blocks, the unavoidable physical behaviors of the universe. So, if we strip away all the complex chemistry and miles of piping, everything is driven by just 3 basic physical traits. The first one, resistance. Think of a kinked garden hose or a heavy doorway. It's a restriction that opposes flow. But here's the absolute key takeaway for your control strategy. The moment that restriction opens, the flow starts immediately. Literally zero delay. It's an instant reaction. Next up, capacitance. And this is the exact opposite of instantaneous. Capacitance is all about storing mass or energy, like a massive water tank or a heavy steel reactor absorbing heat. Because it stores energy, the system won't just jump instantly to a new level. It slowly climbs, and that climb is inversely proportional to its size. So the bigger the tank, the slower the climb. This is where time really enters the equation. The third trait is inertia. This is caused by actual physical mass in motion that violently resists any sudden acceleration or deceleration. Imagine trying to stop a heavy spinning bicycle wheel with your bare hand. No way, right? In fluid systems, when you combine a capacity fed through a resistance, like filling a massive tank through a tiny valve, you get a process lag. The system slowly creeps to a new equilibrium instead of snapping there all at once. Moving on to Section 2, Reading Process Response Curves. This is where we translate that physics into screen trends. The shape a process draws on your screen tells you exactly what's hiding inside. See a smooth, immediate response to a step change? That's a first-order system. It reliably hits exactly 63.2% of its total change in one-time constant. But if you get a deceptive, flat start followed by a delayed, slow S-curve, you're dealing with a higher-order process. That flat start means you have multiple storage elements chained together. And listen, if you try to tune a higher-order system aggressively, it will oscillate like crazy. The controller thinks nothing is happening during that flat start, overcompensates, and then bam, the process wildly overshoots. You have to tune these guys conservatively. All right, Section 3, Essential Control Loop Vocabulary. Let's learn to speak the language of the control room. You absolutely need to know these 4 exact terms to survive out there. PV, or process variable, is what's actually happening in the field, like the real temperature. SP is your set point, which is your target goal. OP is the output, the controller's calculated electrical command. And MV is the manipulated variable, the physical hardware actually doing the work, like a valve. Think about it like this. If your OP is screaming at 100%, but your PV isn't budging, you've almost certainly got a stuck MV out in the field. Section 4, 4 process control nodes. Let's look at the different philosophies for automated regulation. You generally choose between 2 main active modes here. First, you've got your crude on-off control, kind of like your home furnace. It's either completely on or completely off. It lurches around, causes continuous cycling, and puts huge wear on mechanical parts. Fine for a water heater, terrible for an industrial gas compressor. For the serious stuff, you need modulating control. This acts like a continuous accelerator pedal, making super smooth adjustments. And that pedal, that's your MV, adapting on the fly. This modulating closed-loop control is the brain of every PID loop. It constantly runs a 4-step sequence. First, measure the process variable. Second, compare it to the set point to figure out the exact error. Third, calculate the new output signal. And fourth, manipulate the valve to correct the process. Then, it just loops over and over again to fight off any process drift. Section 5, Measuring with Industrial Transducers. Bridging the physical and digital worlds. Because, let's be real, none of that software logic matters without eyes out in the field. You have to match the process variable to the right sensor. We use thermocouples or RTDs for temperature, strain gauges or capacitive sensors for pressure. For flow, you might see orifice plates or non-invasive ultrasonic meters. And level uses hydrostatic or RF admittance.
But here's a really cool industry secret. Pressure transmitters are the absolute workhorses. They actually secretly feed flow and level loops all the time by using differential or hydrostatic pressure to cleverly infer those measurements. Pretty smart, right? But that brings up a really fascinating paradox. What if your sensors are perfect and your PID software is flawlessly calculating the exact OP to match the SP, but the process is still wildly out of control? Which brings us to Section 6, Sizing and Selecting Valves, the final point of physical contact. When your PV is erratic, but the software is doing everything right, you don't have a code problem, you have a hardware problem. Usually, it's an oversized control valve. People love to add massive safety margins when designing systems, so they end up buying these huge valves. But an oversized valve spends its whole life barely cracked open. The slightest output movement causes massive flow changes. You get severe hunting, violent shattering where the valve literally slams against its seat, and accelerated wear and tear. It gives you incredibly touchy, erratic control exactly when you need precision the most. So how do we fix this? Not by detuning the controller, that just masks the symptom. You fix it with a defensive sizing rule of thumb. Always select a valve so it operates comfortably between 0.8 times its minimum CV or flow capacity and 1.2 times its maximum CV requirements. Size it right in that 80 to under 20% window and your physical hardware and digital software will finally play nice together. I'll leave you with this. Control rooms today are getting packed with AI, neural networks, and crazy advanced auto-tuning algorithms. But can perfect software ever truly compensate for an oversized valve or a fundamentally flawed process design? Can a line of code actually outsmart the physical laws of resistance, capacitance, and inertia? Definitely something to think about. Thanks for tuning in to This Explainer.